Welcome everyone. In this video I'm going to show you how to work with 4 to 20 milliamperes signals and how to process these signals with an Arduino Nano and how to display these values on a small OLED display. So everything which is needed can be found on my table, and I will start with a little bit of history of this thing. So what is happening here is that in industry they use this kind of 4 to 20 milliamperes standard. So this means that your sensor emits 4 to 20 milliamperes current, which then converted into a voltage by a resistor, and then this voltage is then measured by some sort of voltmeter, an AD converter or a multimeter or some other specific hardware. And then this current or voltage is proportional to the signal which is coming out from the sensor. So for example, you can have a temperature sensor or a pressure sensor or something like that. And then let's say thermometer's temperature range is converted into a current range in between this 4 to 20 milliamps. And then that 4 to 20 milliamps is converted into a voltage level by using a resistor. And then this voltage level is finally converted into a temperature, which can be read by a human. So I replicate that here in this kind of simulation, and I will try to show you some kind of circuit and some practices how you can do this. So let's start with the power supply, which is on the left side. So here I just have my laboratory power supply, positive red and negative black clips. And the positive one goes into a 2 kilo ohm potentiometer, so a variable resistor. And then I take the wiper, so the output of the potentiometer, and that goes to this red clip, which continues its way to this multimeter, which is set into current measurement mode. So it's in series with this circuit. So then the black wire comes out from the multimeter, continues its way back, and goes into this small network of 2 resistors and the Zener diode. And then at the other side of this circuit, we just use 2 wires to forward this voltage, which is now a voltage as a signal, to the Arduino Nano. And then the Arduino Nano measures this voltage with one of its analog pins. And then inside the microcontroller, I wrote a small program which puts some information on this OLED display. And what I will do here is that I will monitor the current coming out from this potentiometer. So this will basically simulate this 4 to 20 milliamps device, and I will try to measure it. And then I also use the other multimeter, which is here on the 2 sides of a Zener diode, to measure the output voltage, because I measure the output voltage with a, let's say, reliable multimeter, and I will try to compare that with the value which I can read with the Arduino Nano. And there will be some practicalities which I want to share meanwhile I demonstrate everything. So that will be one part of the experiment. And I also want to show you the source code, which is written for this tiny system with one microcontroller and a display, just to see how the conversion works and how we can make these things a bit more better. So on this side, which is basically the measuring circuit, what happens is that there is a 220 ohm resistor in this side, and I will actually share this drawing down below on my website. So please visit the link in the description to see this more better. So this 220 ohm resistor takes this 4 to 20 milliamps current, and by using the Ohm's law, it converts the 4 milliamps into 880 millivolts and the 20 milliamps into 4400 millivolts. So we have a range between 880 millivolts to 4400 millivolts. So this is our range. If you want like really round numbers and utilize the full range of the AD converter in a bit better way, then you can pick a 250 ohm resistor, which is, as far as I know, not a standard value, so I could not find it in my kit. But then the lowest level, 4 milliamp, will be converted into 1 volt, and the 20 milliamp will be converted into 5 volts. So that's maybe a bit more convenient, but hey, we have microcontrollers, they can do the math, so it doesn't really matter. But here comes one of the first practicalities, is that whatever kind of, let's say, nominal value you have, just please measure your resistor and use that value, because here you can lose some precision if your value is a bit off. So then in series with this circuit, so continuing in series after the current junction, let's say, towards the Zener diode, I have a 100 ohm resistor, and then towards the ground part, let's say, so down here, we have a Zener diode. And this Zener diode has the role of, let's say, chopping off the voltage. Then the voltage would go above 5 volts. So this would sort of save the input of the AD converter on the Arduino Nano. So sometimes people say that this is not really necessary, because this 4 to 20 milliamps system will never run out of the range. But some people say that, oh, we need it. So yeah, it's up to you at the end. I just put it here, but you can remove it. And also sometimes people claim, I just don't have the knowledge to really be sure about this, but there can be some leakage current coming from the Zener diode, which can shift your voltage readings. So that can also cause some problems. But as I said, I don't have 100% knowledge about this claim, so I cannot confirm or deny it. So then we have the two poles, the positive and the negative, and then I'm using this multimeter here to measure the voltage coming out from my, let's say, converter circuit, which converts the amperes to volts. And then the voltage continues its way towards the one of the analog inputs on the Arduino. And then I do some calculations on the Arduino and display some numbers on the circuit. So let's power up everything and let's do some experiments. So first I power up the Arduino and let's see what happens. So we have two values here, and on the top I'm showing the voltage in millivolts, and at the bottom I'm showing the current. So now, as you can see, these are 0 here because there is no power coming. So I turn on my 5-volt power supply. And as you can see now, we have 1 volts here at this point, 1.07, and we are measuring 1.06 with the Arduino. So that's for me acceptable. And then currently the current which is flowing from my let's say 4 to 20 source is 4.7 milliamps or 4.8 milliamps. It's fluctuating a little bit, and here you can see that now I'm reading 4.82 milliamps, so that's not so far from the truth. And now I try to twist the potentiometer and increase the current a little bit. I have a bit bad quality potentiometer, so it's a bit hard to work with it, but it works. So now we have almost exactly 2.5 volts coming out here, and we are also measuring almost exactly 2.5 volts, and that concludes 11.3 amps here, and this shows 11.2 amps or 11.3. It's fluctuating again. So yeah, we are very close with all these values. Here comes the next practicality. So here I measure, I told you to measure the value of the resistor. And what you should do here is that once you assemble your system and you picked your power supply for the Arduino, measure the 5 volt voltage on the 5 volt rail or 5 volt pins on the Arduino Nano, because that can be different from 5 volts. For me, it is 4.6 something volts, using my mobile charger as a power supply. And that causes some troubles if you are trying to convert the raw bit numbers between 0 and 1023 into like real voltage. So you should be cautious and always measure the voltage and use that in the conversion. I will show it when I show you in the source code. So now this is like 2.5 volts, so I still have some range. So let's increase the current a little bit. So now this is 3.65 volts. This shows 3.64 volts, not too far away. And then that is equivalent to 16.6 milliamps. And here also we see 16.6 milliamps. So you can see that this works pretty nice within the range, even works above the range to some extent. So I can measure 4.6 volts here, which is also measured here, and 21.4 milliamps or 21.5, and here I measure 21. So yeah, this works. And now I cannot turn the potentiometer anymore, so this is like maxed out, and I can try to touch my resistors. I can feel that this resistor, the 250 ohm resistor, is a little bit warm, but there's nothing to worry about. If you are worried about, you can replace the resistor to a higher wattage rating resistor, but yeah, this is just fine. I can keep my finger on it, I pinch it, and it doesn't burn my fingers. So it's fine. So I just randomly turned the potentiometer 1.41 volts on the output of this circuitry. The multimeter shows 6.4 milliamps, and here we measure also 6.4. So we can do this. And now, as you can see, what happens here first is that I convert the raw bits between 0 and 1023 into a voltage, and then that voltage is basically mapped into current. So it's converted back, because of course we cannot measure current directly. So what we do is we convert the current into voltage, which we measure here, and then we convert it back to a current value here by basically a calibration. And now what you can do here is that you have your current range between 4 and 20 milliamps, and you know that, for example, your pressure sensor is between 0, you know that your range for the pressure sensor, for example, between 0 and 250 bars. So you know that when you are measuring 4 milliamps with your device, that corresponds to 0 bar, if everything is like ideal. And when you are measuring 20 milliamps, then you are also measuring 250 bars. And then anything in between is basically divided based on the resolution of the AD converter. So in this case, the 250 bars is divided to 1023 parts. So that's quite a good resolution, I would say, for like normal everyday stuff. But of course, you can use an external AD converter, 16-bit AD converter like this, ADS 1115. You have much higher resolution, and then you can resolve the 4 to 20 milliamp at a much finer scale. And that makes your reading more precise if you want to have more precise readings. So this was basically the whole demonstration that I wanted to show you. So here again on the left side with this potentiometer, I was simulating the 4 to 20 milliamps, and then I changed the 4 to 20 milliamps, and that was converted back to a voltage by using this 220 ohm resistor, and then that voltage goes into the analog pin of one of the analog pins of the Arduino. And then I do some magic inside with the software and I display some numbers. And maybe one more thing that I can show you is I max out the things here a little bit. Right now we are measuring 4.8 volts, and then I increase the current or the voltage which is coming here. Now it's 5 volts, but now I changed it to 7 volts. But as you can see, the Zener diode does its job and it chops the voltage. So now I'm running 9 volts, but we are at 5.1, and this is a 5.1 Zener diode, so it works properly. So it saves my Arduino, and now I choose another value here, and you can see 980, 970, and 4.4 milliamps, 4.4 milliamps. So this was the what I demonstrated just right now was the capability of this Zener diode. So I was using this 5.1 Zener diode to save the input of the AD converter here. So this was the demonstration part, and now I go to my computer and I show you what is happening on the microcontroller and how you can do a bit more and what I did here. So let's go to my computer. So we have arrived to the Arduino code, and this will be a very short code. Actually it is below 100 lines. So first of all, what we have to do, we add the wire library because the display was using or is using I2C. So these are the pin connections, but of course, once again, go to my website and you will see the drawing for it, but this is written here as well. And then for the display, I'm using the Adafruits library for this display. So this is basically just a copy-paste thing. You don't have to change anything. And then I have a few variables here, and since I was not really concerned about the memory using and things like that, I defined everything as a float. So what I do here, I have the current, and how we get the current between this 4 to 20 milliamps is that we map the voltage values which appear on the analog input. And then we have the raw AD converter value, so that will be a value between 0 and 1023. So 0 corresponds to 0 voltage and 1023 corresponds to 5 volt here. And then the ADC voltage is a voltage between 0 and 5 volt by default. This is now independent from the circuit that we are using. And I added another variable here because I mentioned that you can use this with a pressure sensor, so why not do a calculation or an example with this. And in this example I'm using the A1 pin as the ADC pin. So what happens in the setup is extremely simple. This part of the code is just waiting for a response from the display, and if there is no response from the display, the code gets stuck here, so we are looping forever, and it just sends the message to the serial port. And in fact I have to start the serial before this, so I just move this here so you can actually see if something is going wrong with the display. And here this is nothing else, it's just nudging the display, so I can see that something is happening, but in fact this can be removed if you really want. So the setup can be just simplified to this part. Then loop, what we do in the loop, we iterate over and over. So we start, we read the ADC, and then once that is done, we have the values, so we print those values, and then again we read the ADC, print it, and this goes over and over. So first let's look at this part. So basically this is what is happening in the AD converter. And what is happening here is the following. So first we make sure that this ADC value is 0, because this will actually contain a huge sum of numbers. And the way I wrote the code, which you will see in the following lines, is that we always add some number to the variable. So if we would not make this 0 here, we would have very incorrect readings. So we have to reset the value. So what I do here, as you can see, I run this for loop 100 times, and what I do here is that I have this raw ADC value in the first iteration, which is now 0, and then I add the analog reading to this 0 in this line. So this becomes, let's say, 512. And then I wait 5 milliseconds here, just to let the AD converter settle. I haven't checked what number I should use, but this leads to good numbers already, so I just kept it as this, but maybe it can be even shorter. So then we waited 5 milliseconds, we go back to this part. So this now contains 512, and now we read again and add it to this 512. And let's say we read 514 now. So now the raw ADC value contains 1026, if my calculation is not wrong. So then we have this 1026, and we wait 5 milliseconds again, and then we go here. And when we are in the third iteration, now this is at this 1026, and then the next reading is added to this sum. And this grows and grows until we reach 100 iterations. So now the for loop exits, so we are here at this line. And then we divide this huge sum with 100, so we get the average reading value of the 100 readings. And then we multiply this with the voltage, which we can measure on the 5-volt rail of the Arduino, expressed in millivolts here. So I'm using millivolts, but you can use volts as well. You just put a dot here, but I'm using millivolts. And then I divided it by 1023, so with the resolution of the AD converter. And then this line will actually give you the ADC voltage. And then what I'm doing here is that basically I just use the serial printing. And first of all, I just show the raw value, which is already the average value, so there is a division here. And then I also print the converted voltage on the serial port. And now comes the current value determination. And as I said, I'm using a 220 ohm resistor because that's what I have at home. So then we have to do the calculation with the Ohm's law, and we check the lower boundary, which is 4 milliamps when it comes to current. And if we are at the low boundary or bottom value, then 880 millivolts should be measured at the output of our, let's say, converter circuit. And then when we are at 20 milliamps, then of course this is 5 times this value. So we are reading 4400 millivolts. So when we are using 220 ohms, the lower boundary is 880 millivolts and the upper boundary is 4400 millivolts. And then it's a bit more simple when you use this non-standard 250 ohms. Then yeah, the math is simple. So 1000 millivolts or 1 volt at 4 milliamps, and 5 volts or 5000 millivolts at 20 milliamps. And as I wrote it here in the note, you should actually measure these values. Even if you have a good tolerances or whatever, just measure it. It's better to use. So you exactly know that here you might expect, I don't know, 892 millivolts, and here you would expect 4323 millivolts when 20 milliamps should flow. And based on these values which we calculated here, we can use this mapping function, which is defined down here. So I'm not using the original map of the Arduino, let's say, libraries, because that cannot use the float, and I need float. So what I do here is I just redefine these longs. Originally these are longs. I just use them as floats. So what happens here with the map is that we take the ADC voltage as an input parameter, and the ADC voltage is between 880 millivolts and 4400 millivolts, and this kind of range has to be translated into a current which is between 4 milliamps and 20 milliamps. So what happens basically is that when we measure this current is the output, so that's the value of the current, and we measure this voltage, then this current is the value of the current variable. And then if we are somewhere in between, then this will be also somewhere in between, as I wrote it in this example. For example, if the measured voltage is 2640 millivolts, which is the middle of the range, then we should be also in the middle of the current range, which is 12 milliamps. And then after all these calculations, I just print the current. And then what happens here is that I just do, this is just an example, it has nothing to do with the display at this moment, but just to show you how you can do this with basically any kind of values, is that now we know the current, and we know that these industrial sensors work with current between 4 and 20 milliamps. So what we do is that we need this part. So we figured out the value of the current, and then we know that the current's lowest value is 4 milliamps, and the highest value is 20 milliamps. So we want to map this range into, let's say, pressure, what I did here. So then I know that when I measure 4 milliamps, then there is no pressure, let's say, and that is 0 bar. And then when we are at the top of the range, when the pressure sensor sends out 20 milliamps, then that corresponds to the highest measurable pressure level in the sensor, which is 250 bars. So now this kind of range is translated into this kind of range. And then I just print this on the serial terminal. And basically that's all. Then finally we have to print everything on the LCD. So what I do, I clear the previous contents. Then I set the text size to 3. By using 3, I can print 2 lines on this 128 x 64 OLED display with reasonable font size, and it's quite readable. So I'm using 3. If I would use 2, that would be too small, and 4 cannot be fitted under each other. So then I just set the text color to white, because you can invert the display, but here I'm using it in normal mode, so it's white pixels. So the illuminated pixels will be the text what you see. And then I put the cursor on the top left corner, so that's the beginning of the display where you start printing the text. And then I just print the ADC voltage. And this just sends, this line just sends the value to some sort of a buffer. But what you do here is that you pick some of the variables that you want to print in the first line and write it here, like I did here. So I calculated the ADC voltage in this part. So this has here some sort of value, and that value is put in the argument of this display.println, and it's printed. And then I move to the next part where I can start printing my new text, and this is starting at y equals 40 pixels in the coordinate system of the display, and then I print the current, as you could see in the demonstration. And yeah, basically that's all. After this is done, I have to run this display.display function, which actually sends the content of the buffer, or whatever it is called, on the display. So you will see the actual numbers, the ADC voltage and the current. And if you have any other kind of calculations, like pressure or temperature or something, you just use that variable and put the variable here or here, and that's all. And yeah, finally this map float, it's basically the original float function. It's the original. And then finally this map float function is the original map function of the Arduino. I just replaced the long variables into float, so I can work with yeah, floating point numbers. And basically that's all. So this is the code. It's really simple, and you can hopefully customize it if you follow my explanation. But if you are not succeeding with it, just leave a comment in the comment section and I will try to help you. So I hope that this video was helpful to you. I hope you learned something. Don't forget to visit my website, curiousscientist.tech. You will find all the resources, the circuit diagrams and everything for this project and many more projects. So please check my website, and see you in the next video.